talked about exponents. Now we'll talk about logarithms, but keep in mind they are not different. Logarithms are exponents. So write in your notes, underline it, highlight it, whatever. Say it out loud, even if it sounds silly. A simple sentence might guide you to success with both exponents and logarithms, and that's important. You can pause and look at these if you like. We'll get through them by the end of the lesson here. Natural logarithmic function. Well, why does it say natural? The reason is, let me grab the pen here. The reason is the Euler constant. Remember, that's about 2.718 and so on. It's sort of like pi in that respect. It doesn't repeat, it doesn't terminate. Not only that, it's a little bit more than just irrational. Square root is one thing, this is even beyond that even. And there are more of those than there are square root types, or root types. Here's your common logarithm, and it's called the common logarithm because the base is 10, the number that we use for almost everything. The thing to remember is this. If you see something like this, we'll make this a common logarithm to begin with. And let's suppose we've got some number we're finding in the logarithm. I will call it x. Let's suppose that logarithm was y. One of the big things you want to be able to translate backwards and forwards, and that's not that difficult, is, first of all, look at the number that's at the bottom here. Think of it as being in the basement. Basement, base. Start by writing the base. Next, what's the exponent? Well, if you remember, logarithms are exponents. This and this are exponents. So y is the exponent. What's it equal to? What's equal to the only thing remaining, the x. Translated, what does this exactly mean? This means if we take and use this as the base, what exponent would we need to end up with the x? That's what the logarithm notation represents. Now we're going to use the natural logarithmic function a lot because e is used quite a bit. It just shows up, it seems like everywhere sometimes. Remember that if we look at this, if we've got a special situation where e is the base, because that's used so often, we give it a special shortcut or nickname, ln. This part is the same as ln for natural logarithm. No different. If for some reason you wanted to write this as that, there'd be no problem whatsoever. Keep in mind, though, that what this means is you've got a logarithm to base e, that's sort of understood. What exponent does e need to give you x? This is equivalent to this, because it's got that special base e. B is the exponent, because logarithms are exponents, and x is the number you get if you take e to that power. Two things to keep in mind are that those two functions, e to the x and natural logarithm of x, are inverses of each other. That means that if you take a number x, take e to that power, and then take the natural logarithm of the result, you end up with x all over again. Or another way of putting that is, if you take the natural logarithm of e to the x, you just get x. Well, why is that so? Well, this part right here says logarithm to base e. E to what power gives you this? Well, it's right there in front of you, x. It's that simple. Second, it's the same thing as if we reverse it. E, and this time we'll put the natural logarithm of x as its argument. What do you get? X. Think those through, look at them occasionally until they make total sense to you. Here's an example of that reflective property. In the last slide, if you noticed, it said that those two graphs excuse me, of the inverse functions are reflections of each other around y equals x. You get this line. If you take one of these graphs and fold it over y equals x, you get the second graph. Or if you start with this graph, fold it around y equals x, you get the other graph. That's what it means. Got some properties of natural logarithmic functions. You can review those. One important thing I want you to remember is the x-intercept. If you remember, for e to the x and a to the x, I said these basic functions both go through 0, 1. Well, these are inverse functions, which means their x values and y values are reversed. So for the exponential functions, 0, 1, the logarithmic functions, 1, 0, just reversed. Keep that in mind. Excuse me. So how do you graph these things? Well, we've got two examples. In this first one, f of x equals natural logarithm of x plus 1. Remember, x and 1 are added first, then we take the natural logarithm. We find what power of e would give us x plus 1. Just a reminder. How do you graph it? Well, there's a couple of things you can do. First of all, you can start by graphing several different numbers to get a feel for what it looks like. Use 0 for x because it's easy. Use 1 for x. Different x. Notice you can use this negative only because you're adding 1 to it before the natural logarithm actually works on it. Get several of those points and you can graph it. Another thing you can do is, if you know what the natural or the logarithmic function looks like, the logarithmic function is going to, see, we've got 1, 0, there's our point, and it's going to look something like that. So if you know that's the basic look to it, this is a small translation. This is a translation left to right. And because it's a plus 1, that means the original natural logarithm of x, you could get this graph by taking this and moving it 1 unit to the left. 1 unit to the left. So if you could graph this one, grab a hold of it, pull it to the left 1 unit, you'd have the graph of this new one. On the second one, again, graph a bunch of points, get a feel for it. What's it going to look like in general? Well, if we look at this part right here, we could start with our basic natural logarithmic function. Looks like this. A minus 2 in there means move that to the right by 2. And then this means that all the points you had originally are twice the original value. So that'll stretch it. So there's the first one. Remember, this is right here, natural logarithm of x plus 1. Notice that this was the original right here. We moved it to the left one. There's our graph. Oops, went too far. For the second function, let's grab that. Should have written that twice there. The domain of that function. The easy thing to do to get the domain is, first of all, you know the natural logarithm argument, that's what they call this, has to be positive. So if you know this has to be positive, set the argument greater than 0. Solve for x, and there's your domain. Oops. There. Let's see what the argument is. What does it have to be? For a logarithm of any kind, it has to be positive. So set that argument equal to 0, or greater than 0, excuse me, and solve for x. There's your domain. You get a bunch of different points, and there's your graph. So the original graph looked like this. Because the x minus 2, that moves the graph to the right 2, and this will make it go higher, faster, because every original y value will be 2 times as much. Some properties. Again, important things, because what you're going to do is take some equations and solve for x. So you need these properties so you can do those manipulations to find out what x is. Now, we know the inverse function, they're inverse functions. That means the function of the inverse and the inverse of the function both give you x back again. In other words, they undo each other. You might find it handy, I'm not directly suggesting it, but it might prove handy if you just memorize this. Where these are doing the opposite. Natural logarithm and e to some power are opposites. They're inverse operations. You can do it both ways. Either way, you end up with the original number again. Keep that in mind. Now we've got 3 simple properties. What's the most important thing to remember? Exponents are logarithms. If you remember that, and the logarithm of a product. So if you think of it this way, look at this. Let's suppose we have the logarithm of 2 to the 6th times 2 to the 7th. Because we're multiplying, we can add those two. Remember, this is the same thing as 2 to the 6 plus 7. And logarithms are exponents. So you get 6 plus 7, or 13. If you can get this one down, if anything is the most important of these three, it's this one. Now, this is multiplication, so you'd expect division to be similar, but a little bit different. So since you're dividing, just like e to the 8th or e to the 3rd, subtract the exponents. So since logarithms are exponents, you'll be subtracting the exponents. Remember, logarithms are exponents, so if you're dividing, you'll subtract the exponents. If you forget, make a small example for yourself like this. Now this third property is one you have to be extra careful for, because x times y, add the exponents, you got that? And this one, you take this n and bring it out front. If you get something to a power, you bring that power out front. So you have n, natural logarithm of x, or if it's any other kind of logarithm, the n still goes out front. Don't get these two mixed up. Very important. And what we're going to do is we're going to rewrite them sometimes to solve logarithmic or exponential equations. Sometimes we'll need to expand the logarithm expression. Expanding it means, for example, we'll go from this one to that one. It becomes bigger. But sometimes we need to do the opposite, condense it. That means we go from one like this to one like that. Now I've got four examples here. And let's take the first one. Notice that we've got division, so we're going to be subtracting. So we'll have the natural logarithm of 2, or 10, excuse me. Remember, this means what exponent does e need to give us a 10? We're talking about division, so our logarithms will be subtracting, and that'll be the natural logarithm of 9, which means what exponent would e need to give us a 9? Now if I'm going to expand this, I can actually do a little bit more, because remember, logarithm of 10 is 2 times 5. So what I could do is write this as natural logarithm of 2 plus the natural logarithm of 5 minus. Now what can I do with this one? Remember, this is 3 squared. So I could bring this 2 out front, and I'd have 2 natural logarithm of 3. That could really be expanded. On the next one, a little bit of rewriting might be handy. Natural logarithm of x squared plus 1 to the 1/2 power. Bring the 1/2 out front. Well, 1/2 the natural logarithm of the x squared plus 1. Now you can't take this any further because this is a plus in here. If this were a 10, you still couldn't do anything because it's the plus. Logarithms are all about multiplication, remember. They're shortened exponents or shortened ways of expressing multiplication. The third one, notice on this one, you've got multiplication and you've got division. So I'll take this a little bit faster. If I look at the top two, I'm multiplying them, so it'll be the natural logarithm of x plus the natural logarithm of y, because I'm adding the exponents. I'm dividing by 5, so it'll be minus the natural logarithm of 5. And there's your expansion of the third one. On the last one, I've got multiplication. So I'll have the natural logarithm of x squared plus the natural logarithm of x plus 1. Make sure you put the x plus 1 in parentheses. And you show this as a plus. Now notice before we leave this, this has a power. So you can rewrite this one as 2 times the natural logarithm of x, and then the natural logarithm of x plus 1. Notice especially, this is not the same as the natural logarithm of x plus the natural logarithm of 1. Not. And there are answers. And that's our final answer. And that one, part way, and the rest of the way. Or D, multiplication, property 1. But who cares what the name of the property is? In a different book, it might be a different number. Bring that 2 out front, and you've got your expansion. Now, we can use those to solve exponential logarithmic equations. Now, there's a good reason for being able to solve these. Sometimes, if you have an exponential equation, you might be stuck and you can't solve it the way it is. But converting it to a logarithmic equation, it becomes easy. Or vice versa. Perhaps you have a logarithmic equation and you can't solve it the way it is. But converting it to an exponential equation makes it child's play, and that's what you want. So to solve one, isolate the exponential expression. You'll see that happening. Then take the logarithm of both sides and solve for the variable. A couple of examples will be handy here. So, for this first one, we've got e to the x equals 5. We're going to switch that to a logarithmic equation because having this x up here keeps us from solving it. So we're going to convert it to a logarithm. Notice there's e here as a base, so natural logarithm is the way to go. So, natural logarithm. Now I've got 3 things to write down. I've got a base, well that's understood. You don't need to write this down, but it's got a base of e. Remember, logarithms are exponents. What's the exponent? X. Where's the 5 go? Right there. Start with the base, write down what the exponent is, and there's only one place left for the third one. All you need to do is grab your calculator, find the ln function, put the 5 in, hit enter, and you got your answer. Second one, 10 plus e 0.1t equals 14. This is where we start isolating the exponential expression. So we'll subtract 10 from both sides. That way the expression with the t in it is isolated. Then with this, we'll do as we did back here. We've got a base of e, so I'm going to use natural logarithm. I'm going to rewrite it as natural logarithm. What is the base? Well, we already decided the base was e, so we used natural logarithms. That's already taken care of. The exponent goes over here because logarithms are exponents. There's your 0.1t. And what goes over here? The 4. Now, don't worry about this. You could throw it in your calculator and find the natural logarithm of 4. You don't need to right away. What you can do is look at the right-hand side. If you're solving this equation and just looked at the right-hand side, you'd multiply both sides by 10. So 10 natural logarithm of 4 equals 1t. And that's what you want. Now put it in the calculator and you've got your answer. Put this. There goes the 10. Convert it to a natural logarithm equation. Change it there. And you get your answer. So how about the other way around? Let's take a look at some of those. So first one, natural logarithm of x equals 5. It looks like we're stuck. No, we're not stuck. We know the base of this is e, so I'm going to convert that by rewriting it. First I'll write the base. What does the base have for an exponent? Well, logarithms are exponents. So 5 goes there. Where's the x go? Right there. All you have to do is put that in your calculator and you'll find out what x is. I'll leave that to you. Second one, 3 plus 2 natural logarithm of x equals 7. X is in here. We want to get this part, this term all alone, so we'll subtract by 3. So I have 2 natural logarithm of x equals 4. Notice that both sides are divisible by 2. Might as well do that. Make it look simpler. Okay, now we're ready to roll. But the x is stuck here inside the natural logarithm function. How can we get it out? Very simple. Rewrite. This natural logarithm function has a base of e, always starts with a base, e. What's the exponent? Well, logarithms are exponents. So the 2 goes up here. And of course, there's only one place left for the x. Throw this in your calculator and you got your answer. In fact, e squared might be the answer you want to keep. If it's part of a bigger problem, leaving it as e squared might be a better deal. Okay, finally we get to an application. So, you've got a few extra dollars. You don't need them right away, and you figure they ought to be working for you. So you put P dollars into an account with an annual interest rate of R, compounded continuously, how long will it take for the balance to double? Well, first of all, just a reminder, if you're working with compound interest, the basic formula looks like this. And just a quick review, this is the amount that's there at the end of t years. Sometimes it's called the future value, sometimes it's called the maturity value. This is the amount, the present value that you put in there. It's called the principal, and that's with a PAL. And that's just a 1. This is the annual rate, and it's unlikely that you would see some other kind of rate being expressed, but this is the annual rate. N represents how many times a year it's being compounded. The N also goes up here as a factor in the exponent. And T, you must remember, is the number of years. So if someone should try to throw you a curveball and give it to you in 4 months, you have to convert the months to years before you can use this equation. However, notice this isn't one of those. This is one where the interest is compounded continuously. That's a different formula. It's derived from the first one, but it's used often enough that you actually want to know this one separately. This future value equals the present value times e to the r times t power. R to the base in the exponent. This is in years. Make sure it's in years. So how long will it take for your balance to double? Well, give that a little bit of thought. If the balance is going to double, that means you put P dollars in, and what do you end up with? What you end up with is 2P. Pretty simple, right? So, what can we do? Take a look at that. I can divide both sides by P. So I got 2 equals e to the r times t. Now it says, how long will it take the balance to double? Let's see. Well, I can't solve it the way it is. I'm going to have to switch it to a logarithm. What kind of logarithm? Natural logarithm, of course. So I'll have the natural logarithm of the left-hand side and the natural logarithm of the right-hand side. I'm going to switch those two around. It's not necessary, but just to make sure that there's no confusion here. Now, I would leave this as natural logarithm of 2. I wouldn't actually put in the calculator yet. Next, I've got the natural logarithm of e to the RT. Wait, didn't I just see this a minute ago? Natural logarithm and e to a power are inverse operations. So when I do this, I'm going to end up with RT all over again. And that's equal to the natural logarithm of 2. And that 2 is because we're doubling our money. If we were tripling our money, if you go back here, this would actually be a 3. But what we want is how long would it take? So we need to solve this for t. Very simple. If this were a 7 here, you divide both sides by 7. It's an r. So you divide by r. And there's your answer. Notice, by the way, this is not the same as the natural logarithm of 2 over r. It's not. So when you put in the calculator, for example, if you've got the annual rate, make sure it's in the denominator all by itself. So either make it a fraction and make sure it looks like this, or if you had a TI-83, for example, you could write it like that too. And you solve that, you can find out how long it takes. And this should look familiar. We divide by the p, and take the natural logarithm of both sides, and the inverse property, and then divide by r. That's a slightly different look, but you know it's the same thing. So you can see that's how you can find the time it takes for the balance to double. It's inversely proportional to the interest rate. This is interesting to look at. Just spend a minute, maybe or two, see what happens for doubling times at various rates. So in case you're not quite sure, this means if you go to the bank and the bank says, we'll give you 3% annual interest, you're going to have to wait 23.1 years before your money will double. However, if you go to the bank further downtown that offers 7%, you'll only have to wait 9.9 years for your money to double. Or go to the next town where they're offering 12%, you'll only have to wait 5.8 years until your money doubles. And there you go. So keep an eye on what kind of compounding it is and what the percentage rate is. Even if you see one bank has 7% and the other one has 7.1%, in the short term it won't make too much difference. But if you're able to leave that in there for 20 or more years, for example, it could make a big difference. So keep that in mind, please. Remember, those are the doubling times. And there's a picture of the doubling time and the interest that you just saw back here. Little graph. In other words, look for that high interest rate. So it won't take as long for your money to double. And that's all, folks. Keep smiling, and we'll see you next time when we talk a little bit more about exponents and logarithms.